I hate talks that begin with apologies, and yet I'm going to begin with two apologies. The first is that whenever I'm invited to give talks to not completely physics audiences, I always start with this ambition to speak in the language of the people I'm talking to and to engage with their concerns, and it's never yet actually come true, so it's not going to come true this time either. I'm just going to give you a straightforward, more or less physics talk. It went blue. That happens. The other apology is that I don't even really have a conclusion. It's sort of a grab bag of things. There's a problem, we don't know the answer to it. I have certain predilections about how the problem is going to be solved, but we'll see. We don't know the answer yet. So, three things. First, I'm going to lay out what the general framework in which I'm thinking about the arrow of time and entropy and how it relates to cosmology. This is where the sort of philosophical stances will come in, but I'm just going to state them to you. I'm not going to try to defend them to you. We can certainly talk about them. And then I want to talk about some things that we've learned, or at least some ideas that have become more palatable in cosmology over, let's say, the last 20 years, because I think that we really have made progress in ways, in cosmology, in ways that really should impact on how we think about trying to solve the arrow of time problem, and maybe they haven't impacted as much as they should. And finally, some of my own favorite theories and ideas for how we're going to get there. Again, it's an incomplete thing, but we're making progress. So everyone knows why there is an arrow of time. It's because of entropy. And yeah, this is a picture of entropy. This is Alan Guth's office at MIT. Alan Guth is famous for two things. He invented the inflationary universe scenario, and he won a contest sponsored by the Boston Globe for the messiest office in the greater Boston metropolitan area. So that picture appeared in the Boston Globe. It looks like it's in thermal equilibrium, but every time you go in there, the entropy has gone up a little bit. So maybe he knows something we don't. Anyway, we think that, at least to a good approximation, the laws of physics describing microscopic things are reversible, time reversal invariant, and yet the world is not. If we assign this thing called entropy to macroscopic systems, we find that it goes up. There's an inequality in the second law of thermodynamics. Entropy either increases or remains constant in closed systems as a function of time, and we would like to explain that. So my working assumption is that basically there's only one thing to be explained, that all the different ways in which there is an arrow of time are ultimately due to the same thing. So the fact that we remember one direction but not the other, the fact that we can causally affect one direction rather than the other, the fact that there's a lower entropy in one direction, the fact that we age in one direction, all of these have a common explanation. And I do sometimes, in a burst of enthusiasm, state this belief as everything is explained by the thermodynamic arrow of time. And then David gives me a hard time and says, you shouldn't say that. And so I try to be more careful. And both the thermodynamic arrow of time and all the other arrows of time are explained in a common way. This is a wonderful picture from Roger Penrose's book. Roger Penrose is also famous for two things. He's a mathematician and a scientist. He's also an artist. So he draws these wonderful things. Our environment here on Earth is very far from thermal equilibrium because the sun is a hot spot in a cold sky. If we get an amount of energy from the sun and we radiate it back into the universe, we radiate the same amount of energy back to the universe that we get from the sun, but with 20 times the entropy. For every one photon we get from the sun, we radiate 20 photons in the infrared on average back into the universe. So that's a little pump of entropy that enables all the wonderful things like eating and chewing and aging and philosophy conferences and so forth. And we understand why this happens. We have an understanding given to us by Boltzmann in the 1870s. Here's Boltzmann's tombstone in Vienna. And there's an equation on the tombstone. When I have physics audiences, I say, so what is going to be the equation on your tombstone? There must be some analogous philosophical thing, but maybe it's not as compact notation. What will be on your tombstone? So Boltzmann's tombstone encompasses the idea. Boltzmann was a believer in atoms at a time when atoms were not popular, and he says, if you accept atoms, then I can explain entropy. I can explain what it means. It's the number of ways I can rearrange the constituents of a system to leave the system macroscopically indistinguishable. So we have this space of all possible states of our physical system. We can divide it up according to macroscopically observable quantities. and there might be some microstates that are very similar to many, many other macrostates, many other microstates. They look the same macroscopically. Those have high entropy. It's actually just a logarithm of the number of states that is the entropy. And some are very special. Some, if you change them even just a little bit, they look different, and those have low entropy. And so from that point of view, it makes sense to us that entropy increases as a function of time, because there are more ways to be high entropy than to be low entropy. If you start in some low entropy state, that's relatively finely tuned, delicately arranged, whereas high entropy states are easy and robust, so it should not be surprising that entropy increases. But of course, that's only half of the story, and the other half is not yet completely fleshed out. To explain why the arrow of time happens in the real world, we need two things. First, Boltzmann's understanding of entropy is a counting of the number of macroscopically indistinguishable microstates. But we also need what David calls the past hypothesis, the idea that sometime in the past we began in some very particular kind of state, not randomly chosen, a state with very, very low entropy. If you start with low entropy, then yes, it will go up. But that's an assumption outside the dynamical laws. You can't prove that assumption just using Boltzmann's ideas. So the second thing is a problem for cosmology. One way of saying it is, given that the entropy today is very far from its maximum value, it makes perfect sense to us that the entropy tomorrow will be higher. It makes no sense to us that the entropy yesterday was lower. The real reason why is ultimately traced back to the fact that the entropy was low at the Big Bang 13.7 billion years ago. Now, Boltzmann did understand this. He didn't always admit that he understood it. Sometimes he acted as if, you didn't need this extra hypothesis, but he did, deep down understand it and tried to explain it. And the explanation that he gave, which was sort of the most respectable in terms of it didn't cheat, it didn't put in any assumptions that he claimed he wasn't making, was this one. In 1895, he invoked the anthropic principle and the multiverse. We tend to think of the anthropic principle and the multiverse as modern, crazy ideas with people who have, left the sort of Enlightenment project of grounding science in reason and experiment, but Boltzmann did it. So what he says is, he didn't know about general relativity or quantum mechanics. He says, imagine Newtonian mechanics, absolute space and time, but imagine that the universe is full of particles, of atoms, with a non-zero average density. So there's an infinite number of particles in an infinitely big space, but the density in any one region is likely to be some number. And he says, what's going to happen? Usually, you'll be in thermal equilibrium. That's the high entropy robust state. Remember, you have Newtonian mechanics, so there's no beginning or ending to the universe. There's no Big Bang. The universe lasts forever. Any one region will usually be in thermal equilibrium. That's the high entropy state. But, he says, there's an anthropic criterion. We don't live in thermal equilibrium. We need that picture that Penrose drew. We need departure from thermal equilibrium to live. And therefore, he says, there must be there in the universe, which is in thermal equilibrium as a whole, and therefore dead. That's the anthropic principle. Here and there, relatively small regions, the size of our galaxy, because he didn't know that there were more than one galaxy, but he says the galaxy is called a world. And these regions, during the relatively short time of eons, deviate significantly from thermal equilibrium. So here's a plot of the entropy of a box of gas. Now, because he's Boltzmann, he knows that the second law is not all by itself. It's not absolutely true. It's usually true because we start from a giant departure away from thermal equilibrium. But if you are in thermal equilibrium, if you're the air in this room, and you wait, there will be small statistical fluctuations downward in entropy, and then you bounce back up. So he says, there are gradients in entropy. You're going up and down here, and we could live there. We could live in the aftermath of some random thermal fluctuation away from the highest entropy state. So he has this multiverse. Most places are in equilibrium. There are small fluctuations away, and occasionally there are large fluctuations, large enough to make the galaxy. And we live in the aftermath of one of those fluctuations. That's his idea. It's not original to him. You can trace it back to 50 BC. Exactly the same picture appears in Lucretius's On the Nature of Things. Lucretius was, like Boltzmann, a believer in atoms when not everyone believed in atoms, and he was trying to explain all this wonderful structure around us. So he says there are thermal fluctuations. He doesn't use that term. He was writing in Latin dactylic hexameter, but basically he says there are thermal fluctuations, and at last, if you wait long enough, you'll make the universe. That's the scenario.